So I'm going to continue our discussion of PCA, doing kind of using the iris data set. And now we're going to use PCA in conjunction with a support vector machine classifier. So as before, we're just going to do data. As before, we're going to do data is equal to load iris. And then we're going to set x is equal to data.data and y is equal to data.target. And then what we're going to do is let's do a PCA. And so we got PCA here. And then we're going to do PCA fit of x. And then we're going to do PCA, we'll say z is PCA transform of x. And then what we're going to do is just plot up the data. So we'll have z, and then we'll do, I don't know why my volume keeps going out, but we got z is equal to, we'll do our first one, right? So we have three different classifications, and so we'll do, this is 1, and then I'll do line width is equal to 3, I'll do color is equal to red, and then maybe I'm going to make a dot here. Sorry about that. And then I'll say this is, I'll do label. We'll call this our A. I don't know what the true names of these are, but we can just do it like this. So we can do A. I'll do B and C. So this is my B. This is my C. And then we'll have blue. I'll do green for here, or blue for these, and then we'll do green for those. And so whenever y is equal to 0, we're going to make it red. Whenever it's equal to 1, we'll make it blue, and whenever it's equal to 2, we'll make it green. And then we have, we'll add our legend. We can do PLT X label. And then we can do here is PCA1. And then I'm just going to put in the parentheses the variance, but I'm just going to do 0.2f, percentage 0.2f, percentage, and then I'll map that in there. So we'll do PCA, and what's the number again? I forget the value. Let me just check my notes real quick. And we have explained variance ratio, do underscore, and that's 0. And then we'll get the second coordinate, which is our y label. And then we have 2 here, and then I have 1 over there. And then I can do PLT show. And of course I had to make, let's make that a big Z. And so we have our data set. So I always did that again. So that's a Y label. It's T label. Oh, I mistyped that. So that's a Y label. So now I have my code, right? I'm just basically plotting it up here, the different data points with different data. And we see our first principal component, we have 92% of the variance, and then our PCA2 component, we have 5% of the variance. So again, what's nice about this is because we've taken our 4-dimensional data set and we've projected down to 2 dimensions, it's easier to visualize and make sense of. Now, of course, our principal components are different, basically, linear combinations of our original coordinates. That's what the transform does. It transforms an x value into a z value. And the z value is kind of our new coordinate system. So I could do something like PCA transform. And then if I have something that's solely in the x dimension, so 1, 0, 0, 0, what we're going to see is the return that this is mapping into the new direction is -5, -4, so on. And I can look at what the y, or the second coordinate, maps to, and I get different values. I can get my third coordinate, and I'm going to have different values, and then I could have my fourth coordinate, and I'll have some other kind of value. There's a lot of -5s and 5s because everything's basically projecting down to the first 2 dimensions, and the smaller dimensions have a smaller weight. All right, so once we have this going, maybe we want to design a classifier based on the transform data set. So first thing I'm going to do, set z is equal to tilde, and then I'm going to do tilde comma 2, and I can take a look at the shape. And here basically what I'm doing is grabbing the first 2 kind of columns from my z data set, so I don't have to do it again. So then I could do support vector classifier is, I could do support vector classifier. We'll do kernel is equal to linear. And once I have that, I could do SVC fit, right? And so I'm going to take in Z and Y, right? So Z is my new data set. And then once I have this together, so what I can do is kind of plot this up into 2 dimensions. And here I'm going to play kind of the trick I did before. So first of all, let me grab all my data points down here so I can plot it up, right? And I'm going to get rid of the legend. And what I can do is, if I look at the range, I'm basically going from, like, let's say, XX is equal to NP mesh grid, right? And we're going from basically, let's go -4 to 4, or -5 to 5, and I'll do 1,000 points here. And then I'll do YY is NP mesh grid. And let's see, basically I'm going from like -2 to 2. And maybe 1,000 data points there. And then what I can do is, let me call this is Z, let me call this is W, and we're going to do SVM or SVC predict, right? And then I'm going to take the column stack, so I'm going to do NP column stack, and I've already done this for you guys before. And then double quotes, and then I'm going to do XX ravel. And then I'm going to do YY ravel. And that basically takes the array and converts it to point. And then once I have that, I can say W is equal to W dot reshape. And then I'm going to do XX shape, right? So that's kind of the shape of the vector. And then what I can do is do PLT, P color mesh. And then I'm going to have XX, YY. I have my W, which is the predicted values. Then I have my CMAP is equal to jet. And then alpha, which is just basically how transparent it is. Let's do 0.5. And what did I spell? Ravel. Let's see. What am I doing wrong here? So I have XX, YY, mesh grid. Oh, I see what I did wrong. I forgot to do the NP lin spaces here. Sorry. So this is my, let me come back here. I got ahead of myself. So let me do it like this. This is why it's coming off, because mesh grid returns 2 coordinates. So I'm going to do from NP lin space from -5 to 5, 1,000, and then I'll do NP lin space from what did I do? -2 to 2, and I'll do 1,000 points, and let's close that off. Now I run it. It's going to take a second, and now I can see the classifier, right, in 2-dimensional projection, where I have the red for the green one, so it does this kind of strong line. Then I have my blue, and then I have kind of the red data points. So the nice thing about kind of projecting our data, so remember when we came back here, our data X is 4-dimensional, so there's 4 columns, so there's 4 coordinates that explain kind of the Y values. And what we do is project that down to 2 dimensions, and when we do it, we see that we don't lose a lot when we approximate the 4-dimensional data as 2-dimensional data, because we get probably 97% of the information contained in the 4-dimensional data can be also contained in 2 dimensions. Once we have the 2 dimensions, what we can do is basically do a classifier based on those 2 dimensions. So we're actually building a classifier on a smaller data set, and then we can put it all together and kind of visualize it. And the nice thing about here is we can visualize the classifier. Right here we have 3 classification rules, and basically because we're doing a linear one, it's just drawing straight lines that kind of separate our data. But we also see very clearly that there's a fairly clear separation. There's a couple points that aren't perfect here, but definitely between the red and the blue we actually have a very clear separation. And this is what the support vector classifier is doing. And so this is a nice way to kind of visualize data. So I think PCA is actually one of the more useful tools, at least in my experience, whenever I've done any kind of data problems in kind of taking large data sets and reducing it down to smaller data sets that we can visualize. And that's kind of the power of principal component analysis. And then we can, of course, apply different kinds of classifying rules based on the projected data. It's important, again, to recognize that when we're projecting our data down to 2 dimensions, we're losing information. In this case, we're losing about 2% of the information. Many problems, even though they're multidimensional, can be accurately represented with just 2 or 3 dimensions, but not every data set. So you really have to look at the explained variance ratio to determine how well PCA works. And with that, I'm going to stop. And if you have questions, please post them in the comment section. Thank you.